An integral with an infinite limit of integration may seem like an abstract concept. However, there are real-world applications that require us to be able to evaluate an improper integral. In this video, we will study 3 applications where it's necessary for us to evaluate an integral with an infinite limit of integration. The first is in the area of statistics regarding the standard normal distribution. Calculus-based statistics can involve the evaluation of improper integrals. The standard normal distribution, which you may know as the bell curve, is given by the function f of x equals 1 over the square root of 2 pi times e to the negative x squared over 2. This is actually the curve that I used to generate the graphs on your notes on the previous page. Although this function may be unfamiliar, you're probably familiar with the bell curve. Maybe you've had the luxury of having a professor that grades on a curve, or maybe you've even studied such things as the distribution of human height or the distribution of standardized test scores. There's lots of natural phenomena that follow the standard normal distribution or the bell curve. The bell curve is centered over the mean of mu equals 0 with the standard deviation sigma equals 1. So if you look at the graph below, you can see that it is centered at 0 and the unit of measure on the x-axis is 1. So each unit on the x-axis represents a standard deviation either above or below the mean. The probability that a data point lies above the mean is given by the integral from 0 to infinity. Notice we're dealing with an improper integral with an infinite upper limit of integration of the function describing the bell curve dx. This integral happens to converge and the value is exactly 0.5. In fact, the integral from negative infinity to infinity of 1 over the square root of 2 pi times e to the negative x squared over 2 dx is equal to 1. On the graph, there is actually a horizontal asymptote on the x-axis, so the extreme left and right-hand sides of the curve lie just above that horizontal asymptote. However, the area between that curve and the x-axis is finite, and in particular, it is 1. Because this graph is symmetric about the y-axis, half of the area is on this side and half of the area is on this side. Now, in studying calculus-based statistics, these types of integrals are used to calculate probabilities regarding the standard normal distribution. Maybe you have that class in your future. And maybe you've had algebra-based statistics. The big idea with a population that is normally distributed is that it has central tendency. Most of the data points fall towards the center. So for example, if we're talking about standardized test scores, most people who take a standardized test, such as the SAT, will average somewhere in the middle. The higher the score, the fewer the people, and the lower the score, the fewer the people. So that's an example of a place where an improper integral is used in real-life applications. Let's look at another area of application. How about rocket science? That sounds pretty interesting. The energy required to launch a rocket from the surface of the Earth to an altitude h is given by the integral from r to r plus h of k over x squared dx. Notice the variable of integration here is x, so the integrand is a function of x. That means k is a constant, and in particular, k is a constant which includes the mass of the rocket, the mass of the Earth, and even the gravitational constant. Capital R is also a constant. It's equal to 6,370 kilometers, which happens to be the radius of the Earth. And then finally, h is also a constant, and that's the altitude to which we're going to launch the rocket. And this is also measured in kilometers. So let's see if we can use this integral to answer the question. How much energy is required to launch the rocket to an arbitrarily large altitude h? Now remember, the energy required to launch the rocket to a specific altitude is defined by this integral. So we want to look at an arbitrarily large altitude. So we're going to assume that h is approaching infinity. So we need to calculate the integral from r to r plus infinity, or we can just call that infinity, of k over x squared dx. Notice this is an improper integral because it has an infinite upper limit. So we need to make it proper using our limit operator. So we'll introduce our limit operator and a new upper limit, let's just call it b. So we'll calculate the integral from r to b of k over x squared dx. Now let's evaluate the integral first. That's the first operator we need to execute, and then we'll determine the limit. So we'll carry the limit operator, limit as b approaches infinity, of the integral from r to b, and let's think of this as k times x to the negative 2 dx. Now, do you remember x is the variable of integration, k is a constant. So when we integrate a constant multiple of a function, that constant multiple filters through to the antiderivative. If we integrate x to the negative 2, we would end up with x to the negative 1 divided by negative 1, and we don't need the plus c because we're working with a definite integral. So I'm going to clean it up algebraically. We have the limit as b approaches infinity of negative k over x, which we're going to evaluate from r to b. The next thing we need to do is apply the fundamental theorem of calculus and evaluate the antiderivative at the upper limit and subtract it evaluated at the lower limit. So plugging in our upper limit, we have negative k over b minus negative k over r. Now, if k is a constant and b is approaching infinity, then the limit of this term is going to be 0. The limit as b approaches infinity of k over r, well, that's just a constant, and the limit of a constant is a constant. So we could say the value of our integral from r to infinity of k over x squared dx is k over r. Recall that k is a constant dependent on certain parameters. R is the radius of the Earth. What we want to observe here is that the energy is a finite number. So this means that there is a finite amount of energy required to launch the rocket to an arbitrarily large altitude h. That says it's possible to launch a rocket to outer space. We already knew that, but here the mathematics show us. So we can say, therefore, a finite amount of energy is required to launch the rocket to an arbitrarily large altitude, which we called h. So there you go. You have evaluated an improper integral with an infinite upper limit to do rocket science. So you can go home and tell your families that you did some rocket science today. Let's look at one more application of improper integrals that will affect your very near future if differential equations is in your lineup of courses. We'll examine an operation called Laplace Transform. The Laplace Transform of a function of t, f of t, denoted, we write it with the script L, and we use braces around the function which we are transforming. This is given by capital F of s equals the integral from 0 to infinity of e to the negative st f of t dt, if the integral converges. So the Laplace transform is an operation that takes a function of t. Notice we start with little f of the variable t, and we apply this operation which involves an improper integral with an infinite upper limit, and the result is this function big F of s. Now that capital F indicates that we've taken an antiderivative, and notice we've also changed variables. We've gone from the variable t to what we call the parameter s. So this is a transform. You actually already know examples of two transforms. Differentiation is an operation that transforms one function into another. For example, I can take a degree 3 polynomial and transform it into a degree 2 polynomial under the process of differentiation. You also know the transform called integration. For example, I can transform a linear function into a quadratic function under the process of integration. Both of those are called linear transform. So the Laplace transform is a similar process, and that process is defined by this improper integral. This particular transform converts a function of t to a function of s. This transform is used to solve non-homogeneous differential equations involving piecewise continuous functions. Doesn't that sound so exciting? Now, all of this vocabulary may be unfamiliar to you. What we're focusing on here for the purposes of our class, Calculus 2, is just to learn how to execute this transform. What you'll see later on when you take differential equations is that this is a very valid way to solve a complex differential equation. So let's give it a try. Find capital F of s, that is the Laplace transform, for little f of t equals t. So we want to find capital F of s, which can also be denoted the Laplace transform of little f of t. So this is defined as the integral from 0 to infinity of e to the negative st times f of t dt. And in this particular case, our function is t. So we need to find the integral from 0 to infinity of e to the negative st times t dt. Notice in this case, we are not only dealing with an improper integral with an infinite upper limit, but also notice we're going to have to apply integration by parts in order to execute this integral. We have the product of an exponential function and a power function. So in this case, it's convenient to let u equal t. Du then is dt. We'll let dv be e to the negative st dt. Remember, t is the variable of integration, s is a constant or a parameter. So when we integrate, we'll make a copy of the e and divide by the derivative of the exponent, which is just negative s. So we're going to execute a couple of steps all at once here, so hang with me. We want to rewrite this as a proper expression. That is, we want to get rid of that infinite upper limit of integration and convert that into information maintained with that limit operator. At the same time, we want to apply our integration by parts formula. So we have u times v, that's going to be t e to the negative st divided by a negative s, and of course we'll need to evaluate this from 0 to b. And by the way, notice whenever t is equal to 0, u is also equal to 0, so no change there for our lower limit, minus the integral from 0 to b of voodoo, v du, that's e to the negative st over negative s dt. And you know it's my practice to wait and evaluate everything together. So before I run the upper and lower limits on this first term, I want to go ahead and integrate my second term here. I notice I have a double negative. Also observe the variable of integration is t. We're treating s as a constant or a parameter. So for ease of understanding what we're doing, I'm going to go ahead and factor that constant s, or 1 over s, in front of my integral sign. Then I can focus on integrating e to the negative st dt. So, continuing our process, we have the limit as b approaches infinity. No change for our first term here. And executing this integral, we have coefficient 1 over s times e to the negative st divided by negative s, remembering that t is the variable of integration and s is a constant. Now we can run the entire thing from 0 to b. Do observe here that our variable of integration was t, which means our limits of integration will be plugged in for t. S, once again, is a constant. So we have the limit as b approaches infinity, we're plugging b in for t. So we have b e to the negative sb divided by negative s. Let's rewrite this as minus, we'll put the s squared in the denominator, e to the negative sb. So there is the antiderivative evaluated at the upper limit. Let's evaluate it at the lower limit. So again, we're plugging 0 in for t, s stays in s. Next, we need to work on evaluating the limit as b goes to infinity. So if I look at the first term, I have b times e to the negative sb over a constant. b is approaching infinity, e to the negative infinity goes to 0. So we have an indeterminate form that we need to manipulate here and apply L'Hopital's rule. As far as the second term goes, as b approaches infinity, e to the negative infinity approaches 0. So that term very easily goes to 0. The product here is equal to 0, and our last term doesn't depend on b, but notice we have the constant 1 over s. So working on our first term here, we need to rearrange it into a proper indeterminate form where we can apply L'Hopital's rule. There's a couple of ways to do this. One of the easiest ways I see to do this is simply to evaluate that negative exponent in the numerator by moving it to the denominator. And while we're at it, I'm going to simplify this last term here. Notice we need to distribute our negative. That becomes plus 1 over s. Now observe here, as b approaches infinity, we have the form infinity over infinity. That's our green light for L'Hopital's rule. So applying L'Hopital's rule to the first term, we have the limit as b approaches infinity. The derivative of b with respect to b is 1. We have constant multiplier negative s. Here we're going to make a copy of the b and then multiply by the derivative of the exponent. And we have this 1 over s term out here. Now we can go ahead and evaluate that limit. As b approaches infinity, e to the sb goes to infinity as well, and 1 over infinity approaches 0. Therefore, the Laplace transform is 1 over s. We can say the Laplace transform of the function t is equal to 1 over s. So that will be a smaller part in a larger context of solving differential equations in your near future. Let's attempt another Laplace transform. This time we're going to transform the function e to the t. Recall that the definition of the Laplace transform is the integral from 0 to infinity of e to the negative st times the function of t dt. Let's go ahead and rewrite our improper integral in a proper way using our limit operator. This will be the integral from 0 to b. And let's go ahead and combine our exponential terms. Notice they both have a common factor of t, so I could factor out a t and we'd end up with negative s plus 1 when we add the exponents. When we integrate, recognizing that t is the variable of integration and s is a constant, we will make a copy of the exponential function exactly as it is and divide by the derivative of that exponent, which is just its constant coefficient. Then we can plug in the upper and lower limits of integration. And remember, these limits will be plugged in for t because t was the variable of integration. S is a constant. So there's the antiderivative evaluated at the upper limit. Here is the antiderivative evaluated at the lower limit. Our next task is to actually evaluate the limit. So notice we have this expression, e to the b times negative s plus 1. E raised to a power will either be positive or negative infinity depending on the sign of that coefficient. We know, just for a visual aid here, if we say this is t and this is our function, we know that the limit as t approaches infinity of the function e to the t is infinity, and the limit as t approaches infinity of the function e to the negative t is 0. So we need to determine the sign of this coefficient. If it's a positive coefficient, then the limit as b approaches infinity will be infinity. The integral will diverge. If that coefficient is negative, then the integral will converge. Well, we're not given any information about s, so we're going to have to make an assumption. This integral will converge provided that exponent is negative. Now, if I solve for s, we would end up with s greater than 1. So if s is greater than 1, that means this exponent would be negative and this limit would be 0. That's the only way that the integral will converge. Simplifying the other term, which is not dependent on b, we have e to the 0th power on top, which is 1. We have negative 1 over negative s plus 1. If we simplify this by factoring a negative out of the denominator, we could very easily write that as 1 over s minus 1. Therefore, the Laplace transform of e to the t is 1 over s minus 1 provided s is greater than 1. The integral converges when s is greater than 1. Now at this point, your focus is simply to learn the operation and practice evaluating the improper integral. Later on, in the context of differential equations, you'll get a better understanding of how this process actually helps you to solve a complex differential equation. So those are examples of where improper integrals are necessary for solving real-life applications, such as analyzing the standard normal distribution, calculating things regarding rocket science, the energy required to launch a rocket to an arbitrarily large height, and in this case, calculating a Laplace transform for the purpose of solving a differential equation.